All right, so welcome everyone. What we're going to talk about is the second section of this chapter, where we're going to talk, like I said, about the standing waves and how that's going to relate to sound. Since for the most part, that's actually a big thing for this type of wave. So we're going to talk about the vibrating string. So as you know, a lot of times we create sound by vibrating something. And that vibration actually ends up creating the longitudinal waves. So if you remember from the animation in the beginning of this PowerPoint with the tuning fork, its vibration actually is what's creating the longitudinal wave that carries sound. So here are some frequencies. You don't really need to know this, but just to kind of give an idea that the C note is defined as the frequency of 262 hertz, and it goes all the way up to the next time you reach C, which is 524. As anyone who does anything with music will know, uh, the letters go from A all the way to G, and then it just repeats over and over. So after you get through the cycle to C, then it just repeats until it gets to the cycle again. So we talked about this before, how you have the, let's say, the three first harmonics that you can create on a string would look like this. This is your first harmonic. It is one antinode, which is half of a wave. So we could say the length is one half of the wave. This is the second harmonic, so one full wave or two antinodes, three antinodes or one and a half waves. And if you remember, we have that equation about the relationship between L and lambda. Now, for those also who don't know, one of the ways that we can actually change the frequency on the string, because right now the string is fixed over here at the bridge and over here at the neck, by placing your finger somewhere along here will actually change the length of the string. So what this does is it changes the frequency. This is why pressing your finger on a guitar string will change what note is playing. Yeah. So one thing is when we say that the harmonics are being created, or when we say this, so when we pluck a string and we're saying, hey, this is the standing wave that's being created, that's not actually completely true. If you recall, I had mentioned before that any complex sound can actually be broken up into a combination of all the different frequencies that make it up. Fourier's theorem, if you will. The same thing is actually happening here. When you pluck a string, you're not just getting half of a wave like this. You're getting this one, you're getting the second harmonic, the third harmonic, you're getting all of them. Hence why they're called harmonics, because each and every one is being played. Now they're being played all together at the same time with completely different amplitudes, but they're all being played. Now the thing though is that this first harmonic is the only one that you actually hear. So when you pluck a string and it's playing this specific C note, well, that's the one that you're hearing. You're hearing this. This is its fundamental. However, you're also hearing this C note being played at the same time, and you're also hearing the next C note that's being played at the same time. So you're hearing all of these. This is just kind of going back to before about how the relationship between the frequency harmonics and the fundamental, and the frequency, the wavelength harmonics and the length of the string for all the different integers. Now, one thing is that our ears work on a logarithmic scale. So, what we end up doing is with notes, we actually have notes set up not on a harmonic scale where the next harmonic being played is just two, three, four times the fundamental, but we have it playing on what's called an octave scale. Now, what the octave scale is doing is, so this is the harmonic scale. You have the fundamental, 2 times it, 3 times it, 4 times it. The octave scale is doubling it each and every time. So this is how we're actually able to differentiate two notes, is by for the layman people to be able to differentiate two notes is by having the next time that we get to the letter C, it's not just the, 3 times the fundamental value, it's actually completely double the original number, the one before it. So the first time it was 262, the next time it was 524. So that would mean that the next time you see a C note, it would be 1048, and then double that again to get 2096, and so on and so on. So again, this is what we're doing with music, is we're using the octave scale. Now, you don't need to know this for any questions, I don't think, at least. There might be a question on in the textbook about it, but I don't think I put it in any of the homework questions. I just want to throw this in there for those who are wondering how the octave scale relates to the harmonic scale. Basically, it's a much more condensed version of the harmonics where you're constantly doubling it. So a lot of terms are being dropped. All right, so pause the video and work on this yourself, and we'll go over it in a second. All right, so what we want to know is the string for the lowest note, how long the string is. And they tell us that the frequency at the highest end is 150 times that of the lowest end. So one of the things that we're going to want to do is find a relationship between the frequency and the length of the string. But we actually do kind of know that right off the bat, because we know that the length of the string and the wavelength are directly related. So you double the length of the string, you double the wavelength that could fit on it. And we also know, because of the equation V equals F lambda, that when you double the frequency, you actually halve the wavelength. They have an inverse relationship. But we'll just prove this. So the speed of the waves, because it says the constant tension and linear density for both, so we know their speeds are going to be the same. The speed through the highest piano string is equal to the speed of the lowest piano string. So that means the lambda f is going to be true for both. And then we can say that since the note that's actually being played, or the main note being played, is the fundamental, we're going to replace lambda with 2L. Setting the high end equal to the low end, again, we see that there's an inverse relationship. So we just take the 5 centimeters of the high string, multiply by 150, and we get that the low end of the string ends up being 7.5 meters. Now, just want to talk about this. So that's fairly big. That is about 23 feet. That is a huge thing. Now, for those who haven't seen a piano, they're not normally 23 feet. In fact, most pianos tend to be, I would say, probably under 6 feet or so. So, for a piano to actually get a difference in frequency of about 150 times the lowest key without having a piano that's 23 feet, the way they do is actually they have the strings not being constant density and not constant tensions. If you've ever seen the inside of the piano, you'll see that the piano strings will actually be changing in their thickness. So on one end of the piano, you'll have these really thick strings compared to the other end where they're a little bit thinner. In fact, most stringed instruments work that same way because of the whole not wanting to deal with the difference in the lengths in order to get the difference in the sounds. All right, now what we're going to talk about is the wind instruments. So we just talked about stringed instruments, and it's using a lot of the same stuff that we talked about in the previous chapter, which is why I'm not going into too much detail with them right now. But what we're going to talk about is something a little bit different, where we're going to talk about sound traveling in an air column. Now, there are two different situations. There's the open at both ends type of air column, and then there's the what we call a closed air column where it's only open at one end. So air is going to come in at one end, but it's going to come out. It's either going to be open at the other end or closed at the other end. So on an open section, there actually ends up being an antinode rather than a node. So remember how I said that when you're creating a standing wave, there are conditions that need to be met. And I mentioned that for the stringed instruments where they're fixed at two ends, the condition is that there must be nodes at those two ends. Well, for the air column, when we say that a section is open, what that means is that the antinodes have to be at those locations. There actually is a quick little aside that I'm going to mention, and I'll say this is that the antinodes aren't actually exactly at this location. They're actually, I think, a little bit further out. So this is more used as a rough estimate. I'll mention what I mean in a second, but yeah, what we end up having is the molecules moving the most at the ends. So that's the antinodes. You'll also notice that we're drawing them as if they're transverse waves. Remember, they're not. They're longitudinal waves, so they'd be drawn more like this. But this is something a little bit hard to actually visualize. It's a lot easier for us to just treat them like transverse waves. So what you'll notice is when you look at these numbers and this relationship, it actually ends up getting us the exact same thing as the stringed instrument. So when the tubes are open at two ends, the open tube, if you will, we end up getting the same results as a stringed instruments fixed at two ends, which is nice. It makes life easy to know that when two ends are the same, so both ends are open, both ends are closed, both ends are fixed, the relationship's the exact same as what we did before. Now this picture is just showing the pressure. And again, when we switch over to looking at the pressure variation in the air, we'll actually notice that it does look a lot like the fixed at two ends standing wave. So kind of leads more credence to why the relationships are the same. So nothing changes. This is just from the fixed ends at both ends. What's important though is when we switch over to the closed air tube where one side is closed. Now what we end up having is we have a node at this end and an antinode at this end. Now the amount of waves that I could fit, this is a half of a wave because it's going from antinode to antinode. That's half a wave difference. Well, this is just half of this, so that means it's a quarter of a wave. So the distance between the node to the first antinode is a quarter of a wave. Now, if we want to get to the next antinode, well, starting from here, this is the antinode. That's half a wave. Sorry, this is a quarter of a wave. This would be half a wave. So this would be 3/4 of a wave. So going from the first harmonic to the next harmonic goes from 1/4 to 3/4. Then when we go to the next harmonic, it ends up being 5/4. So unlike before where it was going up by essentially half a wave each time, well, it's still going up by half a wave, but we have this initial quarter that's throwing our numbers off a bit. We're going 1/4, 3/4, 5/4. You could probably guess that the next one's going to be 7/4, yada yada yada. Now, interesting thing you'll note if you're looking at the names, you may have noticed that this goes from first harmonic to third harmonic to fifth. That's usually done so that it's relating the harmonic to the number above here. So the first harmonic, this is going to be 1. Third harmonic, this is 3. Fifth harmonic, it's 5. So it's actually meant to make your life easy. The idea is that there is no second harmonic. There are no even harmonics when we're talking about the closed air tube. So when we have the closed air tube, Our lambda, I'm actually changing the letter to M so that you can differentiate it from this. But we end up getting is this is 4L over M. And the frequency also does still look a lot like the original one, where it's still going to be M times the fundamental. But now what the difference is that this M term is going to be only odd numbers. So again, when they say, hey, what's the fifth harmonic, you're going to look at it and say, well, that's just 5 being put in for here. All right. Oh, I want to go back to this, and I want to actually mention that I said before that even though I'm saying, hey, a quarter of a wave is fitting in this tube, 3/4 are fitting in this one, 5/4 is this one, um, that's not super accurate because remember, the antinodes aren't exactly at this location. So this is an estimate, but it's not super accurate. However, there is one thing that will make our calculations more accurate, and that is that exactly half a wave does get added when we go to the next harmonic. So a lot of times, if you're going to do some sort of like lab with this, where you're trying to figure out the speed of sound through an air column that's like fixed at one end, typically what you do is you don't just do one uh, column and then use that to figure out the frequency because this isn't super accurate. What you do is you find the length for the first standing wave, you find the length for the second, and then you take the difference and say that that's half a wave. So that's one of the things that I want to mention is that most of the time, if you're trying to get very accurate numbers, like I said, if the question is more like, you know, hints that it's supposed to be a lab activity, usually what they want you to realize is that using one tube is inaccurate, but taking the difference between two tubes and then realizing that's half a wave will make your results much more accurate. So here is the next question. You can pause the video, work on this yourself, and we'll go over in a second. All right, so they want us to find the fundamental frequency for a tube that's open at both ends and then closed. And then they say the first 3 overtones. So they're using this so that they don't have to deal with the whole difference between, you know, is there a second harmonic or is there not a second harmonic? So they want us to find basically the first 4 frequencies that can be made in that air column. So what we're going to do, we'll do the first one. They tell us 20 degrees Celsius, so we know that the velocity is 343. If it's open at one end, the fundamental is going to be 2 times the length. So we get that the fundamental frequency is 660. So then the next 3 overtones will be 2 times 660, 3 times it, 4 times it. All right. Now for part B, we're going to, the only difference is that instead of it being 2L, it's going to be 4L because remember the fundamental has a quarter of a wave. So it now becomes 330 hertz. And then when we go to find the next overtones, we're going to multiply it by odd numbers. So we're going to multiply this by 3, by 5, and then by 7 to get these ones. So yeah, you can already see that not the frequencies aren't super connected, even though the numbers are very similar because of the fact that we're skipping the odd numbers, or sorry, we're skipping the even numbers. There actually doesn't end up being a whole lot of overlap between the frequencies produced in the closed tube versus the open tube. All right, quality. So as I mentioned before, um, typically sounds that are nice, that are being created from musical instruments, uh, are usually done because there's other harmonics being played, all the other frequencies that are playing along with it, and all this actually makes the sound more full and complete. Typically, if the sounds don't really have a lot of overtones, a lot of harmonics, then we end up having, we consider that as just noise. So again, if you remember, we said before about the principal superposition. You take these harmonics, these frequencies, of just doubling and tripling the frequencies, we get this combination. So what this was being, so these graphs are taking three instruments, a clarinet, a piano, and a violin, and what it was is they're playing the same note. Um, and you'll notice that for the clarinet, actually for all of these, you do see that they are playing essentially equal differences between each one. Now there are some overlaps between some of these. Again, that's the noise. With the piano, it's a little bit harder because of the fact that there's all those other strings that can have sympathetic resonance. We'll talk about that in a second. So the piano is a little bit harder, but if you look at the biggest peaks, you will notice that they do kind of go up by the same amount, by the overtones, like doubling each time. The violin is the most clear, not as many strings, so not as much sympathetic resonance. But yeah, you can see it in here that when you play a single note on a violin or on a clarinet, you're not just getting one frequency, you're getting other frequencies along with it. All right, interference. So if you remember, we talked about how waves can actually occupy the same space at the same time and interfere with each other, combine their results together. Now, there's a really cool effect that ends up happening when two waves that are really, really close, and that is that they will create what's called a beat frequency. So if you have two frequencies that are fairly close together, like in this case 50 hertz and 60 hertz, um, you'll see that the one that's a higher frequency will go through its cycle much quicker. So if they start together, you'll notice that it starts to pull away from the 50 hertz one, and it'll quickly go faster and faster until there's a point where they actually will end up being in opposite directions. So here, the 60 hertz will actually be hitting a crest when the other one, when the 50 hertz, is hitting its trough. So they start completely in phase, but then by the time they hit this moment, they're now in complete opposite phases. They're out of phase. But then as this continues in its high frequency, it slowly starts to recede back with the other one until they come in phase again. So these frequencies are constantly going in phase and out of phase as they come together. And what this ends up creating is, like I said, these beats where you'll get a sound that sounds loud, and then all of a sudden it quiets down and then peaks up again and quiets down. So the sound is something more like a woo, 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 woo. Like I said, a beat essentially, almost like a dubstep. And the beat frequency, or the period of a beat, is the same as the period of anything. It's the time it takes for it to go from one section to the very equal section, the next section. So from when they're in phase to the next time they're in phase, or the time between whoops, as I normally say it. So here, the beat frequency would be zero point 0.1 seconds. Or sorry, the beat period would be 0.1 seconds. If we do the math, that gives us a beat frequency of 10 hertz. Now, if you notice, this frequency is 50 hertz, this frequency is 60 hertz, and the beat frequency is 10 hertz. So it turns out that the beat frequency will actually be the difference of the initial frequencies that we had. This is actually really nice because what this helps people do is it allows them to fine tune the frequencies between two things. For example, if you're trying to tune an instrument, what you can do is you can pluck a string. Like if you're trying to tune a stringed instrument, you could pluck a string and bring a tuning fork close to it. And if you hear the a beat frequency, you can then tighten or loosen the string until that beat frequency gets really, really. One second. really, really low. So you'd want it to make it so that the beats are much more spread out. All right. Oh, I also remember someone mentioning that this ends up being a problem sometimes with airplanes or boats when one engine is operating at a different frequency to the other engine will actually create an effect like a beat frequency, and sometimes it's noticeable to the crew and could end up resulting in damage being done either to the people or to the equipment. So that's also something that happens. Again, anytime you have two things that are operating together, uh, and you're trying to, but they should be operating with the same frequency, and if they're off, you'll be able to notice it. In fact, I'm sure everyone's probably done this. I know I do it all the time, where you put your blinker on your car and you try to pay attention to the signal of the car in front of you. So at first you'll see them blinking together, but then because one of them's a little bit faster, they'll start to slowly get out of sync, and then they'll come back in sync later on. That's kind of what's going on here. So if we're looking at the equation for the combination of the two sound waves, it would look like this. You just take the equation for one wave, add it to the equation for the second wave, and then what we can do is we can actually combine this together using a trig function to get this. One of these is actually going to dictate how the amplitude is changing, and the other one is going to dictate essentially the period. All right. And like I said, the beat frequency ends up being just the difference between them. Now, we're not going to do anything with this. I just want to show you the equation. But we're going to mainly be worrying about this part, that the difference in these frequencies creates the beat frequency. All right. So pause the video. You can work on this, and we'll go over in a second. Alright, so we use the tuning fork held near a vibrating guitar string. The tuning fork we know is going to create 400 hertz, and then we hear 20 beats in 5 seconds. So there are two different possible frequencies, because remember, the beat frequency is just the difference between the two frequencies. So when we use the 20 beats in 5 seconds, we get that the beat frequency is 4 hertz. Now, it could either be 4 hertz higher than the tuning fork or 4 hertz lower than the tuning fork. So, our possible frequencies are either going to be 396 or 404. All right. Another thing with sound is the Doppler effect. So the Doppler effect is the apparent change in the frequency. Now, this is not something that is unique to sound. It's just that this is the one of the ways where that's more noticeable for it. Anyone who's taken astronomy knows that we do have Doppler effect with light and light waves, but normally that's not the most common. You normally only get that, like I said, when you are dealing with the in astronomy or some sort of radioactive plant things. Yeah. But I'll talk about how Doppler effect is affected in light later on. So we're just going to talk about its effect with sound. So what ends up happening is that as a system moves, it will actually change the frequency that that an observer will actually hear. But the object doesn't have to move. The source of the sound does not have to be the one moving. It could also be the observer that's moving. But the main idea is that there has to be some sort of relative motion between the observer and the producer. So you can actually see it a little bit here. So I don't have the animation before, but this is creating sound at a very constant rate. But because it's moving at a relatively fast speed compared to the speed of the wave, what ends up happening is that the next time a wave is produced, it's actually closer to the first wave it produced. So the wavelength actually gets bunched up together. And then on the back, it does the opposite. It starts getting further and further apart. So the in the direction that the object is traveling, or where the relative motion is, the wavelengths get really, really small. And because of the inverse relationship between wavelength and frequency, the frequency that's going to be perceived is going to be very high. On the flip side, the section where it's going away from it, the wavelength gets really large, meaning that the frequency gets really, really small and decreases. All right. This is typically the like when you normally what's the way that you would hear this is, well, like with cars passing by or a train. Like if you ever had an ambulance, rush by you and it goes meow meow. That's a Doppler effect. Whereas it's coming towards you, it has that really high pitch, and then once it passes you, that pitch drops into a lower pitch. So just trying to come up with an equation of, well, what would the frequency end up being that's observed by the person. So here what we have is a source that produces a sound. Now if it's not moving, then by the time the second sound wave gets produced, the first sound wave is going to be over here. Now, remember, these lines are supposed to represent the crests of the waves, or the compressions, if you will. So the wavelength would be this distance between the first one and the second one. But now, when the second one is, or when the source ends up moving, when it moves a certain speed, it's going to cover a certain distance by the time that second one ends up being released. So the wavelength that we end up hearing is going to be this one. So this was the original wavelength. This would be the new one. Basically this plus the distance that the source moved. So what we can do is we could do that. We could say that this wavelength was the full wavelength between the actual original wavelength minus the distance that the source moved. So we could plug in lambda for that, and then the distance for that the source moves, just speed times time. Of course, by the time it moved, it's the time that the next front comes out, so that's just the period of the wave. Then that could be replaced with frequency. Period can be replaced with 1 over the frequency, which is equal to lambda over the speed of the sound wave. So we end up getting this. We could pull a lambda out from both terms and clean it up, and we get this. But wavelength isn't really good. We don't really care about the wavelength. What we care about is the frequency. So we bring it back to the equation for frequency being equal to speed over wavelength. Set in this equation that we have for the wavelength, and then again clean this up. We could replace the V sound divided by the full actual wavelength to just be the original frequency, and we get this. So this is our new observed frequency. This is the actual frequency of the source. And then it's based off of the speed that the source is traveling out and the original speed of sound in that medium. So there's a few things that I want to note again. I want to first remind you that through the Doppler effect, the frequency isn't actually changing. It's only being observed and appearing to change. So the siren is still releasing 400 hertz. The sound is still 400 hertz. It's just that you would hear it to be something a little bit higher. Maybe you hear it as 500 hertz. If the source is moving away, then the only difference is that it ends up being plus. So we end up switching the signs to be plus. If the observer is moving, then it just slightly changes it, where it actually comes up to the numerator. And then if you have both of them moving, it ends up looking something like this. Yeah. And again, you just want to pay attention positive and negative. Positive here, negative up here go together, and that's related to whether they're getting closer. Negative down here and positive down here is for when they're moving further apart. Again, but when the with the moving observer, it ends up being the same idea where it hears this, and because it's moving, by the time it hears the next one, the period that this perceives it is going to be a lot shorter than the original one. All right, so you could pause this video, work on this yourself, and we'll go over in a second. All right, so here we have the police siren. The frequency, when we hear it at rest, we want to know when it's moving at it's moving at a speed of 25 meters per second. So if it's moving towards us, that means that when we do that, we're going to make that that number negative on the bottom. So we plug in the 25, and we're just going to use 343. We get that the frequency that we hear goes from 1600 hertz to 1700 hertz. And when it moves away, we switch that sign to a positive and get 1491 hertz. All right, here's the next one. Pause the video, work on this yourself. All right, so what we do here is first we're moving towards a stationary source. So we're going to use this slightly altered equation where we have this stuff up top, and we're going to have the positive, and we're going to make our observer speed 3.5, and we end up getting that this is the source that we end up hearing. Now, what we end up having to do later on is the frequency that bounces from us will actually be reflected to the other object. And now the thing is, when the frequency bounces off of us, it's bouncing this frequency off of us, and now it's acting as if we're the moving source. So even though the stationary source, the source is technically stationary, now that it's being reflected off of us, we're now the source. So we're going to do this again, which is why I have the double prime here. We're doing this again for a source that's moving, and we're going to use this new frequency to get that the newest frequency is 5103 hertz. So this is actually what the detector ends up hearing. All right. And then using that, we can actually figure out what the speed of the original object was. All right. Shock waves. So this is what happens when an object ends up traveling faster than the speed of sound, or it ends up moving at what's called a supersonic speed, or going a certain Mach. If you've ever heard like, oh, Mach 2, that usually means that you're going 2 times the speed of sound. So this would be enough. So yeah, when you get faster than the speed of sound, you end up creating these shock waves caused by the amplitudes of the sound pulses kind of building on top of each other. A lot of times this can create damage. So if you've ever seen videos of it, or if you've ever seen it in person, of people flying fighter jets, as they pass by, the moment they pass by, you end up hearing this loud cracking sound, and a lot of times glass items will end up start breaking because of the shockwave produced. Yeah, so this ends up being an important thing to take into account, because if you've ever wondered why we can't make planes go faster, like why commercial planes can't go faster, it's mainly because they're trying to avoid this shockwave being produced. Now, there were planes, commercial planes, that do travel at Mach speed. I believe it was called the Condor. However, the thing was that it was only allowed to do it over water. It's actually illegal for a plane to travel to break the sound barrier over land, mainly because of the damage it could do to the things around it. So it ended up not being super viable because distance that it was actually breaking the sound barrier wasn't really that long for it to be a super noticeable. It was like you got to your destination maybe an hour earlier on a 4 hour or 5 hour trip. Not super necessary. So this ended up not being a thing, but there are people trying to find a way to change the way that planes are designed so that they can actually break the sound barrier without creating these shock waves. So that's the next step in our evolution of technology. All right. So this was everything that we talked about. We talked about the moving source for Doppler effect and the moving observer for the Doppler effect. You want to pay attention to the signs. We talked a little bit about beat frequency, and we also talked about these equations. Again, we I didn't put it on here, but we also did mention about the open and closed tubes, and we talked about standing waves again. All right, so this is the next homework for chapter 16. It's going to be due on Monday, and these are the questions on it. There's really not much that I can talk about with these. All right, so the next video I'll post is where I'm going over all the extra problems. If you have any questions, please let me know. Otherwise, I'll see you later.